Cylindrical Coordinate System. In the cylindrical coordinate system, we first define a point. Considering the Cartesian coordinate system with point P located on it, P is determined by length x, y, and height z. In the cylindrical coordinate system, the variables defining a point are phi and z. Here R represents the distance of the point from the z-axis. The range of R extends from 0 to infinity. If a point lies on the z-axis, its distance is 0 and this distance can extend up to infinity. But R cannot be negative. For simpler comprehension, R can be observed on the xy plane. The angle formed between the x-axis and R is denoted as phi, where the minimum value is 0 and the maximum value is 2 times pi radians or 360 degrees. This angle can also be determined from the projection onto the x-axis. As defined previously, z represents the height of the point and range from negative infinity to positive infinity. Thus, a point in the cylindrical coordinate system is defined by parameters r, phi, and z. Now, unit vectors. To define the unit vectors, note that forming the r-axis requires connecting a point to the z-axis to establish r itself, enabling the definition of a hat sub r. Consequently, a hat sub r requires defining a point in the coordinate system. Similarly, the variable phi depends on a defined point because r must first be formed to specify its angle with the x-axis. Therefore, a hat sub r and a hat sub phi are defined locally at a specific point. For instance, taking point P, it is first connected to the z-axis to obtain distance r. Mark a single unit along r in the direction of increasing r to obtain a hat sub r. Projecting r onto the xy plane shows how a hat sub r is represented below. Angle phi specifies the angle between r and the x-axis. Following the definition of a unit vector, arc along the path of increasing phi from the point of interest. Since the variable is angular, an increase in the phi creates an arc. Thus, the unit vector a hat sub phi is tangent to this arc in the direction of increasing phi. As observed, a hat sub phi is perpendicular to a hat sub r and lies parallel to or within the xy plane. Selecting a unit vector along height z determines a hat sub z. Unit vector a hat sub phi can likewise be evaluated directly at the point. The three unit vectors are mutually orthogonal. Define a vector in the cylindrical coordinate system involves specifying components along each unit direction, a magnitude in the direction of r, a sub r, a hat sub r, a magnitude in the direction of phi, a sub phi, a hat sub phi, and a magnitude in the direction of z, a sub z, a hat sub z. A vector is thus defined as vector A equals a sub r a hat r plus a sub phi a hat phi plus a sub z a hat sub z. The component magnitudes are functions that can be constant or functions of any variable. In the cylindrical coordinate system, prior to addressing vector addition and subtraction, an essential point must be considered. Suppose point P1 is defined by three specifications to establish R, phi, and z, where its angular coordinate is denoted as phi1. Assume point P1 serves as the reference for defining our vectors. Now consider second point P2 with specifications R, phi2, and z. That is, point P2 possesses the exact same radial distance r and height z as point P1, differing exclusively in the angular coordinate phi. If we consider point P1 as the baseline, the unit vector a hat sub r1 and the unit vector a hat sub phi1 must be oriented accordingly. However, if point P2 is taken as the baseline, the unit vector a hat sub r2 and the unit vector a hat sub phi2 are oriented differently. As is evident, unit vector a hat sub r1 is not equal to unit vector a hat sub r2, nor is unit vector a hat sub phi1 equal to unit vector a hat sub phi2. Consequently, for addition, subtraction, and subsequently vector multiplication in the cylindrical coordinate system, the location of vector definition must be identical. Specifically, their phi coordinates must match to ensure that the direction of unit vectors a hat sub r and a hat sub phi are aligned, as these unit vectors are defined locally at specific points. Therefore, addition and subtraction are valid only when the vectors share the same point of definition or at least equal phi values. Under this assumption, given two vectors A and B defined at the same reference point, vector addition or subtraction is performed simply by adding or subtracting the corresponding component magnitude along each unit vector direction. Regarding the dot product in cylindrical coordinates, consider vector A and B. Evaluating A dot B requires taking the dot product of each component of A with every component of B. Assuming both vectors share the same phi coordinate so that their directional unit vectors align, the computation yields the dot product of the R component of A with the R component of B equals A sub R times B sub R, because the dot product of unit vector A hat sub R with itself equals 1. The dot product of the R component of A with the phi component or Z component of B equals 0 due to mutual orthogonality. Similarly, the dot product of the phi component of A with the phi component of B equals A sub phi times B sub phi, while its cross terms with R and Z vanish. Finally, the dot product of the Z component of A with the Z component of B equals A sub Z times B sub Z. Summing these non-zero terms given A dot B equals A sub r, B sub r plus A sub phi B sub phi plus A sub z B sub z. Based on this proof, taking the dot product of vector A with itself yields A sub r s squared plus A sub phi s squared plus A sub z s squared. By definition, A dot A also equals the magnitude of A times the magnitude of A times cosine of 0 degrees, which equals the magnitude of A s squared. Equating these expressions yields the magnitude of vector A in cylindrical coordinates as the square root of the sum of its s-squared components. Now, we consider the vector cross product. For the vector cross product, let us again consider two vectors A and B, where the equality of their phi coordinates permits the operation. Evaluating the first component, the cross product of unit vector A hat sub r with itself yields 0, as the cross product of any unit vector with itself is 0. Thus, the first term vanishes. For the second term, evaluating the cross product of unit vector A hat sub r with unit vector A hat sub phi requires applying the right-hand rule at reference point P. Align the index finger with unit vector A hat sub r and bending the middle finger perpendicularly toward unit vector A hat sub phi causes the thumb to point in the direction of unit vector A hat sub z. Consequently, this cross product equals unit vector A hat sub z, yielding the term A sub r B sub phi unit vector A hat sub z. For the third term, taking the cross product of unit vector A hat sub r with unit vector A hat sub z via the right hand rule shows that the thumb points in the direction of negative unit vector A hat sub phi. Thus, this term yields negative A sub r times B sub z times A hat sub phi. For the fourth term, involving the cross product of unit vector A hat sub phi with unit vector A hat sub r, applying the anti-commutative property of the cross product indicates that since unit vector A hat sub r cross unit vector A hat sub phi equals unit vector A hat sub z, reversing the order yields negative unit vector A hat sub z without needing the right-hand rule. This produces negative A sub phi B sub r unit vector A hat sub z. The fifth term involves the cross product of unit vector A hat sub phi with itself, which equals 0. The sixth term involves unit vector A hat sub phi cross unit vector A hat sub z, aligning the right hand such that the index finger point along phi and the middle finger along z positions, the thumb in the direction of positive unit vector A hat sub r. This yields A sub phi B sub z unit vector A hat sub r. The seventh term evaluates unit vector A hat sub z cross unit vector A hat sub r. By anti-commutativity, since unit vector A hat sub r cross unit vector A hat sub z equals negative unit vector A hat sub phi, this order yields positive vector A hat sub phi. This gives A sub Z B sub R unit vector A hat sub phi. Finally, the eighth term involves unit vector A hat sub Z cross unit vector A hat sub phi, which by anti-commutativity yields negative unit vector A hat sub R. This produces negative A sub Z B sub phi unit vector A hat sub R. Taking the ninth cross product term, the cross product of unit vector with itself equals 0, thus all 9 cross product operations are performing. Now, we collect like directional components. There are two components along unit vector A hat sub R. Factoring out unit vector A hat sub R allows us to combine their scalar terms. Similarly, there are two components along unit vector A hat sub phi, so we factor out unit vector A hat sub phi. Likewise, two components lie along unit vector A hat sub z, where unit vector A hat sub z is factored out. This expression yields the complete vector cross product. Alternatively, this vector cross product can be represented using a determinant. The first row contains the directional unit vectors, unit vector A hat sub r, unit vector A hat sub phi, unit vector A hat sub z. The second row consists of scalar components of vector A along each respective direction, A sub r, A sub phi, and A sub z. The third row consists of the scalar components of vector B, B sub r, B sub phi, B sub z. Evaluating this determinant directly yields the exact combined expression derived above. We can also utilize a right-hand cycle permutation diagram to determine cross product. Moving in the positive cycle direction yields a positive result, specifically taking the cross product of a unit vector A hat sub r with unit vector A hat sub phi yields positive unit vector A hat sub z. The cross product of unit vector A hat sub phi with unit vector A hat sub z yields positive unit vector A hat sub r. Taking the cross product of unit vector A hat sub z with unit vector A hat sub r yields positive unit vector A hat sub phi. As long as the cross product follows the positive right-handed cycle order, the cross product of any two unit vectors yields the third unit vector with a positive sign. Conversely, proceeding in the counterclockwise direction yields a negative sign. The right-hand cycle relationship serves as a convenient memory aid to perform the cross product alongside the determinant method to obtain the expanded vector expression.